Good day, my name is Owen Clashing, and today I will be doing an overview of branching and convergence in System Center Opalis Integration Server. Opalis is the newest member of the System Center family of data center products from Microsoft. One of the main strengths of Opalis is the visual presentation of policy or workflow. I will be using the terms policy and workflow interchangeably, but it will always be in reference to Opalis policy. Opalis represents policies graphically. This makes it very intuitive for the IT administrator to visually design a workflow and be able to assess the precedence of operations within the workflow. Unfortunately, this strength in visual representation can also become a weakness in that the design time representation does not always represent what happens at runtime. In this video, Visio diagrams will be used to illustrate what happens when branching and convergence take place in a workflow at runtime. Let's do a quick overview of the legend that will be used. The legend is as follows. The color of the box indicates if the runtime implementation of the object is what is inferred from the design time representation of the object. If the box is white, then what is represented at design time is a behavior implemented at runtime. If the box is yellow, then what is represented at design time is different from what happens at runtime. The green text at the top of the box represents the published data that is available to the current object from previous objects in the workflow. Each term, separated by a comma, indicates a set of published data from the object with the same name. The black text at the bottom of the box represents the name of the current object. It is the name that will be used in subsequent objects to represent the published data generated by this object. The term in red below the box represents the cardinality of the current object, that is, how many sets of published data are created by the current object. This comes into play if the current object is a type of object that can generate more than one set of published data, and the output of the object has not been flattened. Examples of these types of objects are the query database object that returns one set of published data for each row of data returned from the SQL query. Another is the getUser object from the Active Directory integration pact. This object allows Active Directory users to be retrieved based on specified criteria. If the criteria specified results in more than one user being matched, for example, if department is used as a criteria and there are multiple users in the specified department, then each user is returned as a different set of published data. Now on to our scenarios. Our first and simplest scenario is a sequential workflow in which each activity creates one set of published data. That is, it has a cardinality of 1. In this scenario, each object in the workflow has access to all of the published data from the objects that precede it. The flow is simple. The first object, W, is executed, then the second object, X, then the third object, Y, and so on. This means that an object at the end of the workflow can access the published data from all of the objects in the workflow. So, for example, if the last object in the workflow is a send email object, then it can access published data from all of the objects before it. Now that we have dealt with the simple scenario, let's look at something slightly more complex. We will now examine what happens in the case where one of the items in the sequential workflow outputs two sets of published data. Although we use two sets of published data in the example, the same principle applies whether the number of sets of published data outputs is greater than 2. In Opalis, the workflow would look no different from the one in the first scenario. In fact, it would be no different. It is the runtime behavior of the workflow that is different. At object X, the available published data would be that from object W. Object X has a cardinality of 2, which means that it produces two sets of published data. For each set of published data, Opalis creates a branch and launches a separate copy of the subsequent object. This is shown here. The branch is maintained for the remainder of the workflow. It does not converge. This means that, for example, if object Z is a send email object, then two emails will be sent. And each email can have published data only from the object X published data that is in its branch, i.e. X1 if it is in the X1 branch, or X2 if it is in the X2 branch. The last scenario detailed an implicit branch due to a cardinality greater than 1 for an object. In this scenario, we will examine what happens when an explicit branch is created by having more than one successor to an object. We will use a branch to 3 successors. We will converge these branches to a single object. The policy works as expected up to the point of convergence. Object C has the published data from objects A and B available to it. Object E has the published data from objects A and D available to it. Object G has the available data from objects A and F available to it. We expect this because the layout of the workflow implies that A is a predecessor of B, and also of D, and also of F. The visual representation of the workflow implies that the published data from all previous objects will be available to the object at which convergence occurs, object H in this scenario. This is not so. What actually happens is that each of objects C, E, and G regard object H as their successor and will each separately invoke an instance of object H when they are complete. That behavior results in a runtime behavior of the workflow like what is shown here. Each branch results in a separate instance of the object where convergence is supposed to happen. Each instance of the converged object has only the published data from its branch available to it. This can be particularly confusing as Opalis does allow the design time usage of published data from all branches of the workflow. So, for example, if object H is a send email object, at design time, one could construct an email that would be pulling data from objects C, E, and G within object H. Opalis would not complain about it. At runtime, however, 3 emails would be generated. The first with published data from C, the second with published data from E, and the third with published data from G. At no time will object H have the published data available simultaneously from all 3 predecessors. One of the implications of the non-convergence of a branch workflow is that if branching is being done with the intention of achieving parallel execution with later convergence, then this will not work. What will work is doing the activities in a sequential manner, even if there is no requirement that they be performed sequentially. If this is done, then at a later point in the workflow, the published data from the previous objects can be obtained. This last diagram shows an alternative to the previously presented parallel workflow, where all of the objects are arranged in sequence, and the published data flows forward through the workflow and is available to the final object in the workflow. While this may not be the intuitive way of laying out the workflow, especially if objects B and C are mutually independent of objects D and E and are also mutually independent of objects F and G, it works from the perspective that it allows object H to have access to all of the published data from the previous objects. When we take into consideration that Opalis is single-threaded in the execution of any given policy, there is really no significant performance penalty incurred with this approach. I hope this video has clarified how branching and convergence works in Opalis and some of the issues that can occur because of the difference between design time representation and runtime implementation. Have a good day. Thank you.